The Large Hadron Collider. It is near Genova in Switzerland, in Central Europe, which is Southern Europe. It's operated by CERN, and it is built into the in the 80s built Large Electron Positron Collider 100 meters underneath the ground. And it is 27 kilometers long. It is not a circle. It is an octagon, so of 8 sides. And it is the largest machine in the world, and it is cooled down to almost absolute zero, to 1.9 Kelvin. Now, and what happens there? There are strong magnets, strong electromagnetic fields who are kicking protons, one in that direction, the other one in that direction. They're kicking them always, if they pass it with one thing, they're kicking it on to the next part. One proton to that direction, other protons into that direction. And at 4 of these things, there are now other magnets, and they are trying to push them very small together. Protons are very, very, very small, on a very small places, so that actually, when at one curvature, hit exactly the other ones. And then they bang together. Now, and that works, and that the electric resistance of the magnets is not a break on them. They are super cooled down with helium, and also they are superconductors, these magnets. Now, and when they bang them together, then there are things to measure them. There's ATLAS and LHCb and CMS and ALICE. These are detectors. When they bang together, these protons, they are breaking up into gluons and quarks. And because we smash together, and inside of the protons, there are gluons and quarks. And when they are then detected, so first it goes on, there comes then concentric cylinders up in there. The first one is a semiconductor. So in that semiconductor, where the electrons very loosely bound. Semiconductor, you add just one electron, and it can conduct electricity. You take it away, and it does not conduct anymore. Now they come against it, and they are pushing basically at these loosely bound electrons when this semiconductor all them around, and you can see pretty much exactly where they were with gluons and quarks. And the next thing are the magnets, and they're pulling at them, and at the curvature it becomes clear how much they were pulled in, what the momentum of it was. Now, and then it is able to take that momentum at the next cylinder. So there's then at the next cylinder, there's now liquid argon and lead tungstate. And there these are stopped. Gluons and quarks are stopped in that very solid material. And when they are decreasing in speed, these gluons and quarks, they were accelerated, these protons, to 99.9999% of light speed, of speed of light. Now, when we're decelerating these quarks and gluons, then they're emitting photons. And these photons, the momentum can be now seen and calculated back to what mass they had. And the muons, they are going through it. These detectors out of lead tungstate and liquid argon, they are detected later. And the neutrinos, they are not detected at all. But it is able to calculate back what mass they had, because from the photons, how much mass the neutrinos had. No, neutrinos not. The neutrinos, they can be, if all is calculated together, what was measured, the subtraction of the neutrinos. Now the Higgs is the thing where it is calculated back. It is not, the Higgs is decaying too fast. But it is sometimes predicted to be decaying into high energy, a high energy pair of electrons, of photons, a high energy pair of photons. And it can be calculated how much Higgs would be there. Now, and if it's sometimes decaying into these high energy pair of photons, they can again measure it with a momentum and how much energy they had, with the magnets pulling at them, changing the momentum. It can be calculated back, translated back, how much energy that Higgs had, and how much mass it had. And now the Higgs has 125 gigaelectrons. And where the Higgs was discovered with the Large Hadron Collider on the 4th July 2012. And that is the Large Hadron Collider, and that is all according to the Richard Webb's particle physics book on the page 57 and 58. If you click this video away, then please tell me what the reason was, so that I can improve. Otherwise, hi and welcome. I'm trying to learn machine learning. Today, the Large Hadron Collider, mechanical engineering. Today, the Large Hadron Collider, and after we've done it, we're going to do stretching. And if you participate in the stretching, then it's really honest. The LHC, the Large Hadron Collider, extreme machine. At 27 kilometers long, The Large Hadron Collider, LHC, is the largest machine in the world. Okay, it is 27 kilometers long, largest machine of the world. Its most distinctive feature, though, is its temperature. At 1.9 Kelvin, a smidgen about absolute zero, the LHC is the coldest ring in the universe, unless an alien civilization has built one that is colder. So what we're saying is that thing is cooled down, or in it is something cooled down, or the whole thing inside, to almost absolute zero. That is in Celsius minus 270 degrees something. It seems to be that Kelvin zero is absolute zero. So it is at 1.9 Kelvin. Were it not for this searing cold, the LHC might have suffered the same fate as the superconducting supercollider, which was on its way to become the most powerful accelerator in the world before the US government canned it in 1993. The SSC's partially complexed 87-kilometer tunnel near Waxahachie, Texas, now lies derelict, killed by a ballooning budget and a deficit of innovation. Keen to avoid a similar debacle, CERN, the European Particle Physics Lab near Genua, Switzerland, took the momentous decision to cram the LHC into an existing circular tunnel 100 meters underground. And that tunnel had been built in the 1980s for the Large Electron-Positron Collider. Okay, CERN are the people who are running it, or the firm. I don't know if you have somewhere the name for what CERN means, C-E-R-N. But CERN, that is in Switzerland, a country in Switzerland in the Alps. There has CERN its laboratory, its big thing, near the city, I don't know how it's pronounced, Geneva, in Switzerland, where CERN operating this Large Hadron Collider. And they built it on an already existing 100 meter underground existing circle, which they had built for the 1980s Large Electron-Positron Collider. That thing is 27 kilometers long, runs at almost absolute zero, the largest machine in the world. These are the information so far. It was a decision that led to a carefully choreographed dance of extreme engineering. Underground rivers were frozen in mid-flow, compounds shipped around the world, and superconductors pushed to the limits to deliver the magnetic power that would be needed to curve protons traveling at almost the speed of light around such a tight circular path. I don't understand the half of these things. I don't know what you mean with underground rivers were frozen mid-flow. We're going to have the other things on the other page. We needed very good magnets and compounds for them, and also good conductors. The cooling for the magnets requires liquid helium at a temperature at which it is superfluid with zero viscosity that can slip through microscopic cracks. I don't understand that part. If it is superfluid, then it must have a high viscosity. A superfluid sounds like it is superfluid. But viscosity is how much something is able to flow or to stand still. And if it has zero viscosity, that means that thing is almost hard. So it is necessary to have liquid helium. Helium is a gas. And that now in liquid form. So liquid helium, and that whole thing at a temperature at which with liquid helium is a superfluid. It sounds as if it would flow perfectly. Or is a superfluid something with zero viscosity. That would mean that it would not flow. Whatever. It runs on liquid helium. Let's just say with that we don't understand the rest. Liquid helium also, again, at special temperatures. To give it zero viscosity, being then a superfluid. Whatever these words now mean.
The first attempt to switch on the LHC in September 2008 failed after 9 days when a joint connecting a pair of superconducting wires overheated, causing an explosive release of helium used as a coolant, delaying the project for over a year. Okay, we have informations together. What was here? 27 kilometers long at 1.9 Kelvin, almost absolute zero, minus 279 degrees or 78 degrees Celsius. And it is built on an existing 100 meter ground tunnel, which was built for the electron-positron collider. The Large Electron-Positron Collider, it's run by CERN near Genua in Switzerland. The Large Hadron Collider, LHC, at CERN near Genua, Switzerland, is housed in a 27-kilometer long tunnel. It is commonly described as a ring, but is actually more like an octagon with rounded corners. In the straight sections, intense electromagnetic fields kick two counter-circling beams of protons every time they come past, increasing the speed. It is 27 kilometers long. It's not a perfect circle, it is an octagon. So it is with eight sides, not a perfect circle. Now on the straight sections always there are intense electromagnetic fields, and they are kicking the one beam of protons into the one direction and the other one into the other direction. So there is a magnetic field pushing the protons in it into one direction, always making them faster on all these straight ones, and another one into the other direction, always faster and faster. So when we're having protons running in that direction and other ones in that direction. By the time of collision, they have reached 99.999999999% of speed of light. So they're getting faster and faster, and both of them, that would be double speed of light, having the speed of light. Basically, bending such a fast-moving beam of particles requires very powerful magnets. We're having electromagnetic field is doing that, and we're needing powerful magnets to do that. Any power lost to electrical resistance would be a brake on performance, and so the magnets are made of supercooled, superconducting materials. I don't really understand that part. But there seems to happen an electrical resistance if such magnets run on electricity are working, and that electrical resistance would slow them down. And therefore they are cooled down. We try to say it basically just that. We're preparing a presentation about it. So, and there's happening an electric resistance, and to get the electric resistance down, when this electromagnetic field is pushing these protons into the both directions, they are supercooled. They are superconducting materials and supercooled. Superconducting, that means they are conducting electricity very good, must mean. I don't really know what to mean with it, but they are delivering the current very good. Paper or wood or things deliver electrical energy, current very badly. Iron or metal or stuff out of which cables are very much better. Even then they can only achieve gentle curving, hence the LHC's vast size. So it has to be 27 kilometers long to make it able to push the protons, because gentle curving, I don't understand. Whatever, they need 27 kilometers when they have more space to do it. We don't have time left now. We're going to continue the next part of reading the next two sections here. We try to remember all the informations, and then in the next, or the part after the next one, we are trying to do a presentation out of memory about the Large Hadron Collider. If you were here for mechanical engineering, you can go directly to the next part of mechanical engineering. If you stay here and participate in the stretching, then it's going to be almost. The feet are standing together, on the feet, and they're doing the rooting tree exercise. So one toe to the outside, the other toe. The heels and the heels, the toes and the toes. As far as you can go. And now do the. But now stay down, go into the knees. And up again. A bit wider apart, breathe in and lift the arms up. And breathe out and go to the side. Again in and out. Again in and out. One hand slides down the leg. Breathe in. Out one arm up. Breathe again in and out back, and one hand slides down the leg. Breathe in and out one arm up and out. And the feet standing together. Breathe in and lift the arms up. And breathe out, one hand down. Again in and reach. Out and down. In, reach high. Out the other hand down. In and reach. Out and up. And up, down. Legs again shoulder wide apart and shoulder circles. Back, up and front and down. One more round. And backwards. And breathe in, lift the shoulders up. And breathe out, let them fall down. In and up. Out and down. Breathe in, lift the arms up. And reach always with one hand higher. Pretend to take an apple, hang high on an apple branch. Turn it around and rip it out. And legs wide apart, arms up to a T. Breathe in and out and shift with the upper part of the body over to one side. Again in and out over to the upper part. Again in and out. We're leaning onto the knees. The buffalo fighting its hangover exercise. Breathe again in and out, one shoulder in front. Back, the other one in front. Back, and in front. Back, and in front. Back, and out, and we're hanging down. Niagara Falls exercise. Just keep hanging down and breathe in. And breathe out over to one leg. Breathe again in. Out over to the other one. Breathe in. Out into the middle. Close the feet. And the Salto Angelo. Breathe again in. And out. Again in. And out comes slowly with the round back up. Back at the top and backwards. The toes are pointing to the outside. We are having an ulnar length space between the heels. Breathe in and lift the arms up. And again out and sink down. Elbows against the inside of the knees. Breathe in, straighten up. And out and come with the back up. Breathe again in. Out and back. In and straighten up. And out comes slowly in one straight line upwards. Hands again. Have a good standing leg, the heel of a mobile leg on top of the knee of a standing leg. Breathe in. And if you can do it without to injure yourself, sink down. The seahorse pose. And up again and change. Breathe in. And out. Up again. Legs wide apart, the breathing in and going down. And breathe again out. Again in. Out. Breathe in. And out. In. Out. Breathe in and close the legs. And breathe again out. It was a stretching. I thank you very much and until next time.